right, welcome to another session of DGX Compare. Today we're going to be working with llama 3.1. This is the 70 billion parameter model, quantized 4-bit. But one thing cool about this model today is that we're actually running it clustered. So here I have two DGX devices. To the right is the DGX Spark, and to the left is the Acer GN100. They're both the same platform with the Grace Blackwell GB10 chips. This monitor is hooked up to that to that Acer device, the GN100, and this monitor is hooked up to that Spark. I'm monitoring the memory of this of the GN100 on this monitor, and you can see the processes kind of running there, refreshing itself. It's kind of annoying, but it's there. Let's go ahead and also turn on the activity monitor. There it is. It's in the background. But we're tracking that right now. Right now, current usage, spiky. Nothing's really happening yet. And there are all the cores. Let's make this a little bigger. All right, just so you can see. All right. It's currently sitting, again, it's a shared pool, so 256 gigabytes of RAM. It's currently sitting at 95 and 7% utilization. And on this side over here, I just want to see, it's not very often you can see it, but here, let's do a quick query, Docker exec query. So there you can actually see the combined memory, 175 gigabytes, and then 72 allocated for KB cache. And again, these are 128 each, but there is overhead, right? So, but yeah, let's go ahead and refresh it just to make sure. Yep, there it is, 170.25 of actual usable memory, and then 72 for KB cache. We have this monitoring the actual bytes that it's being transferred, and here we have the application actually running. All right, so on Open Web UI, we're going to go ahead and do our typical query. Tell me about Tyrannosaurus Rex, and now let's monitor the tokens per second. All right, let's move the activity monitor over here. Where's that activity monitor? Oh, there it is. Let's move it there. So it's still thinking right now. This is a really big model, so it's going to be slow, but I'm surprised that it's this slow because normally the prefill stage of the inference is actually really fast, or much faster on this device than it would be on a MacBook, even though it has a higher bandwidth, like 3 or 4 times higher bandwidth, but the prefill is just much faster. The cores are running, not too heavy. The packet size is moving. And over here, yeah, it's 170. So this is the worker node. Nothing's really happening there yet. The expectation is that when we utilize the memory on this Spark, and then eventually it's going to run out or just get hyper busy, it's going to transfer all the work or some portion of the work over to this device. So we're not doing anything over here, right? But you can already tell that the memory is already 128. It's already a max. So what's functioning right now is, I guess, Ray is the memory management tool that's part of this Docker container. It's actually sending a bunch of the prefill work over to the worker node, and it's waiting for that information to get passed back to the front end where it's going to be served using Open Web UI. You can see right here all the core usage, right? It's pretty crazy. Look at that. And we got a problem here. It's gone ahead and said the connection is lost. Let's make sure we still have Yeah, it's still good, still connected. Packets are still going. Occasionally it gets flaky like that. Um, and over here, wow. Okay, look at that. See, the mouse isn't even moving anymore. And so I know what's happening here. So at this page right here, this phase right here, it's moving all of the information that it's gathered through prefill. Oh my God, it just crashed the browser. Oh, actually, no, it wasn't. It's actually a Firefox update. Wow, what a coincidence. Um, let's ignore that. That's weird. Okay, there we go. It's more like it. Oh, there we go. So it sent all the information over. Oh man, I wish I would have counted, but essentially, yeah, the pre-fill stage is completed. And now it's actually sending the information back to decode. So pre-fill over there, decode over here. And now you're starting to see more core usage here on this device, or at least, sorry, on this, I guess, node. Um, and there, this is less busy than what it was. But now it's sending all the info there. Now, this is a very large model. Even quantized, it's not great, but I'd say it's probably going, I don't know, 5, 7 tokens per second. 1001, 1002, 1003, 1004. Yeah, it's not great. It's not usable. But I kind of knew that was going to happen because despite the fact that we have 256 gigs of RAM allocated, I only really moved 65% of memory to be used for the model because I wanted to reserve enough context for KV cache. I was previously testing this on a different day and I used 85% and it started crashing after a couple more queries. But either way, I just wanted to show kind of what happens during clustering. So again, over here, the worker is no longer on load because it's not really doing anything, and all the work has been sent over on this side. But memory isn't really moving as much anymore because, again, the hard and heavy lifting has been done already, and that happens during prefill. And now it's just sending off all that data to decode. And there we go, it just finished. Okay, so what I kind of want to show here is, so that's the initial run, right? We just literally turned on the model. So what I want to do next is now that the model's sitting nice and neat inside memory, is it faster the next time around? So let's still watch the processes. Over here, again, very light, very stable on the memory side. There's nothing, a swap is not that much, maybe a gig, 3% worth. But most of the cores are pretty stable there, not doing anything. And over here, same thing. The cores are pretty idle, right? Nothing over 10%, maybe just that one. But now let's go ahead and do another query. Let's check here again and make sure that the connection's still around. Okay, look, see how it's changed? It's now allocated 85 gigs of memory that's available total. And because, again, there's some memory that's being allocated that way as part of the weights themselves. So it's less and less memory and it's available for the actual, I guess, thread, right? The moment you start adding context in, that context is added into KV cache and your memory gets less, okay? It's still decent though. We still have 85 gigs, and the model's been loaded in. So we're going to click the next button here. It says, how did the T-Rex's binocular vision contribute to its hunting abilities? Before I do that, let's get that activity monitor up as well. There we go. And we'll click that button and see how it goes. So I clicked it. Oh, look, see? The prefill is much faster now, right? Earlier, it took some time to get loaded into memory, but look, it's almost immediate. If I was doing this on a Mac Studio, this would take some time, and then it would eventually come. It could be several seconds, but here it's instantaneous. Looking at the cores, again, not as busy anymore, right? Because all of that data is done during prefill, and it's already being done, worked on over here, and it was very, very, very fast. What we're trying to showcase here is that when you have adequate memory, the prefill the first time around is really slow because it's just loading the entire model into memory. But the second time around, when it's already there, the prefill stage of inference is much faster. And again, look at the usage of memory here, very little. Let's see how many bytes are moving. Yeah, packets are consistent. See, no errors, nothing dropped or missed. Let's take a look at the usage. Refresh there. 85, 36. Okay, pretty stable. Let's take a look back over here. Again, nothing's happening, right? Because it's already been done. And system memory is stable at 60 there. Remember, this is 128 over here and 128 over here. I wish I could have that dashboard working for usage of memory. But take my word for it. It's over on this side. What you really care about is the combined memory anyway, right? So we have 85 gigs available. And if this is one unit or one node, it would be impossible because the maximum amount you would possibly have is it's 128. And right here, it's 121 right there. Sorry, 101, right? And again, that's just the cache and the memory itself. There's also other memory that's being used to actually hold the weights, right? Let's do this one more time. So again, over here, look at the graphs, kind of down, not really busy, and the text is done. Let's go ahead and click another button. This one's, what are some of the most significant fossil discoveries? 1, 2, 3, I'll click on it. And then right after I click it, you notice, right? There we go. It starts to spike up. It's already generating the text over here. But it's spiked over here because this worker node is doing all of the work. 100% CPU over there, 31. These two are spiking up, doing all the work. Let's take a look on this side. Yeah, they're two also busy. See, they're taking turns, right? This is working, that is working, combined together. Let's swap, take a look at here for the swap. Same thing, 85, 36, right? It's been stable. And it's generating a text. It's not as bad as before. I guess maybe it's usable. Can I live with it? No, I wouldn't be happy with that. But I guess if you clustered two more, and then you could have 512, maybe it would be a little faster. But I don't think it's going to be that much faster because, again, we're not using that much system memory. I think it's just the DGX memory. It's, I think, 273 megabytes or megabits per second. And megabytes? Yeah, megabytes per second. And it is not the fastest memory. If you want fast inference, you definitely want to go with the Mac Studio at 800 something, or if you could fit the model in, use an RTX system. But in terms of the DGX's job. The DGX's job is to do the heavy lifting, which is doing all the pre-fill work and gathering the information and sending it off to the model to actually show the end user. That load is much, much, much faster. I'm talking like, I think 1,000 or 2,000, depending on how much memory you have. So as you can see right here, see how all the nodes are almost, they're all not spiky because they're kind of tapering off. And then the entire load is sent over here now, because essentially this is the part where you're doing the later stages of inference. And it's done, okay? We'll do this one more time, just for the sake of it, but checking there, okay? See how it's spiked down because nothing's happening because it's done. Same, still stable at 60, GPU utilization, 7%. Let's click on another thing over here. Can you elaborate how scientists determine the growth patterns and rates of dinosaurs like T-Rex? Okay. I'll click on that right there. The signal's being sent. Boom, right there. It just went to 94% GPU utilization. The spike is up there. But look, it's already serving it, right? And it seems a little faster than what it was earlier, right? Yeah, over here, still no packets, you know, still no errors or dropped or missed packets. Everything is stable. Yeah. So anyways, I hope this has been helpful. This is Tensor Parallelism, or Tensor Parallelism, say that 5 times fast, at its finest, and showcasing on a cluster with llama 3.1 quantized to 4 bits, running on these 2 Sparks. Thanks a lot.